Welcome back to our course on memory device technology for AI/ML computing. I am your instructor, Dr. Shubhadeep. Let's try to recall what we were studying the last time. We saw how a rectangular array can be folded into a square array to facilitate better read and write latencies and better power consumption. And this was facilitated by having k pages within the square array, where k was equal to the word length. Having a square array meant that we had equal number of bit lines and word lines. We also saw what is the importance of changing the peripheral design from just a simple address decoder to row decoder and column mux. The row decoder selects the word lines and the column mux selects one of the 2 to the power of m word lines within each page. In addition, we also saw the analog peripherals. We just mentioned what are the analog peripherals, the sense amplifiers and the pre-charge or the write driver circuits. In today's class, we will do a deep dive of the pre-charge circuitry and the sense amplifier, which form part of the analog peripherals. First, we will discuss about the pre-charge circuitry. So the objective of the pre-charge circuitry is to charge the bit line. Please try to recall why we use the term charge the bit line, because although the bit line is one long interconnect, it will have both a resistive and capacitive element. The capacitive part of the bit line is generally represented as CBL, C standing for capacitance. And the idea is that I would like to charge the bit line for a read operation to VDD. And this is done through a pass gate transistor. As you may know, there are several implementations for a pass gate transistor. Since memory peripherals is an area sensitive topic, we would like to have the simplest implementation of a pass gate transistor, which is nothing but a single transistor. However, it is very curious to note that this transistor, which is connecting the VDD to the BL, is a PMOS. In silicon technology, we know that the mobility of holes is generally 1/3 or 1/2 of that of electrons. So for any kind of access transistors, we try to use NMOS. So what justifies the use of PMOS here? The answer is very simple. If we had an NMOS in this case instead of a PMOS, there would be a VTH drop across the NMOS when it was turned on. So if VDD was the voltage at the one end, the bit line would have only pre-charged to VDD minus VTH. And to prevent this issue, we use a PMOS which has no VTH drop. Therefore, it is also natural to expect that the gate will be connected to not enable but enable bar, because only when enable bar is deasserted or made 0 will there be a current which will flow from VDD to BL. However, the actual pre-charge circuitry is slightly more complicated. This is because for a lot of memory devices, especially SRAMs, you would not only have one bit line, you would have a second bit line called bit line bar. What is the need for this, especially during the read and write portions of SRAM, is something that we will discuss very soon. But for the time being, the idea is I need to pre-charge both bit line and bit line bar with VDD. So just like I had a PMOS in the side connecting the VDD to bit line, I have hopefully an identical PMOS transistor or a pass gate transistor PMOS connecting VDD to bitline bar. Let us consider the scenario where, due to process variations, the strength of MTP2 and MTP3 are not identical. If MTP2 is slightly stronger than MTP3, it is but natural to expect that the charging of bitline will be faster than that compared to bitline bar, and therefore there could also be some differential voltages between bitline and bitline bar. Now this could be really detrimental to accurate and effective readout. So to circumvent this problem, we add one more transistor connecting bitline and bitline bar. The rationale for adding this transistor could be understood by considering a very simple example. Suppose we have two buckets, bitline and bitline bar, which we are trying to fill from a water tank called VDD. And these P2 and P3 are two pipes connected from the tank to the buckets bitline and bitline bar. If P2 pipe is slightly fatter than P3, it is but natural to expect that bitline bucket will fill faster than bitline bar. Now that is not what is desired. So what can we do? The bottom of the buckets can be connected through another pipe such that any differential filling between the two buckets can be normalized or can be equalized. That is the simple rationale of having another pass gate PMOS transistor between bitline and bitline bar, to make sure that bitline and bitline bar are at the same potential. This concludes our discussion on the pre-charge circuitry. Next, we will look at the sense amplifier circuit. As we had discussed in the previous class, the sense amplifier is absolutely vital, especially during the readout phase. This is because when we read out, the voltages that develop on bitline and bitline bar are not pure 0 or VDD, which are the contents of the cell, but a small differential voltage. This is because the size of the cell and the associated capacitance is negligible compared to the huge interconnect capacitance of bitline and bitline bar. As a result, when we start the readout circuitry by enabling the word line, there is only a small differential analog voltage which develops either on bitline or bitline bar. The idea of sense amplifier is to sense this small analog change and very quickly amplify it to either positive rail or negative rail compared to the sign of the differential. Also, we discussed earlier that a sense amplifier can be constructed with an open loop op-amp. But that is not a good thing because an op-amp is a very complicated circuit consisting of 20 transistors. Since peripheral architecture is very area sensitive, you would like to build a very simple differential amplifier. And this can be done by putting two common source amplifiers in tandem. So these are two common source amplifiers constructed of transistors Q1 and Q2 consisting of resistors RD1 and RD2. Both have a common VDD and are connected to a common current source. In ideal conditions, where V in1 and V in2 are identical and RD1 and RD2 are also identical and Q1 and Q2 are absolutely identical transistors, you would expect that I1 should be equal to I2, which will be nothing but half of I. Also, the VO1 and VO2 will be nothing but VDD minus I into RD by 2, where I is the total current. However, under these circumstances, if bit line develops a additional small delta V analog voltage, let us try to see how this differential amplifier behaves or reacts. It is very clear if V in 1 becomes slightly more than V in 2, the VGS of Q1 will be more than that of Q2. As a result, no longer I1 will be equal to I2. In fact, the drive strength of Q1 will be more, so I1 will be greater than I2. Current on the left branch will be more than that of the right branch. If the current of the left branch is more than the right branch and these two resistors are identical and both are connected to a common plus VDD, it is natural to expect that the voltage drop on the left branch has to be higher than that on the right branch. As a result, VO1 at this point will be slightly lesser than VO2. Without doing a small signal analysis, which can be looked upon at any analog textbook, we will see that the difference between VO1 and VO2 will be proportional to V in 1 minus V in 2 multiplied by minus GM into RD, where GM is the transconductance of these identical transistors. However, in realistic situations, these resistors are replaced by two PMOS transistors, Q4 and Q3. This configuration, as you may know, is called the current mirror configuration. In the current mirror configuration, similar principles apply, but the resistances are replaced now by transistors. This is important because making accurate resistance on CMOS lines is very difficult. Making transistors which are reliable and identical is much easier. The area occupied by resistors, reasonable resistor, is much larger as compared to a transistor. So therefore, this particular design is much more area compact, and also because there aren't much variations in Q3 and Q4, the offset corrections is much easier compared to the resistor based sense amplification or differential amplifier circuit. In all these things, it is important to consider that there is a very important trade-off between area and speed. As we had discussed in the pre-charge circuitry, the size of P2 and P3 will determine the drive strength and therefore how much current can flow through VDD and bit line. This will in turn determine how quickly these CBL and CBL bar can be charged. So if you would want your read latencies to be smaller, you would expect that bit line and bit line bar to charge faster and the strength of these two transistors P2 and P3 to also be higher. As you know, drive strength depends on the sizing of the transistor. Ion is proportional to W by L. L is generally constant for any transistor technology. So you generally play with the width of the transistor. If you increase the width of the transistor to improve the drive strength, you will compromise on the area. Similarly, the transistors in a sense amplifier also are tuned or can be tuned to give faster response times by increasing their size. These considerations become very important because now we are seeing that not only does your memory chip depend on the size of your memory array, but there is a very strong and important contribution in the memory area coming from the peripheral circuitry also. And in the next session, we will see how a unique metric called the memory array efficiency defines how good the efficiency of the total memory chip is. That we will be seeing in the next class. So, in today's class, we did a little bit of deep dive into two important components of analog peripheral circuitry, which is your pre-charge circuitry and your sense amplifier. Most importantly, we saw that whenever we are designing peripherals, there is a very important trade-off between area and latency. Thank you. Let's meet in the next session.